In exercise 2116, we saw how you could form a lactone. That was a molecule that had an ester that was in a ring. So a carbon double bonded to an oxygen, single bonded to an ether, but in a ring. So an ester in a ring is a lactone. If you have an amide in a ring, so here we have a carbon double bonded to an oxygen with an amine on one side. If you have that in a ring, that's called a lactam. Now, if you have it in this specific structure where it's in a four-membered ring, this shows up in a lot of antibiotics. They're called Beta-Lactam antibiotics. And so I thought it was worthwhile to go through this example of doing a nucleophilic acyl substitution that sort of shows the reactivity of the beta-lactam structure in an antibiotic, in a beta-lactam antibiotic. I thought it would be especially relevant since a lot of people in this course may be pre-health. Okay, so how could you sort of break apart this lactam? Well, you would look at this, you would notice that on this molecule on the left, you have a carbonyl with 1, 2, 3 carbons attached to it. And you still have that here, carbonyl with 1, 2, 3 carbons attached to it. What's different is what's attached to the carbonyl on the other side. In the starting material, we have a nitrogen attached to the carbonyl that gives us an amide, and what we have in the product is not a nitrogen, but a methoxy group, an oxygen. And so the amide turns into an ester. Now the nitrogen is still there, but it's on the other end of the molecule. It's not attached to the carbonyl. So it acted as a sort of leaving group. It was replaced by a nucleophile, and that nucleophile was coming from methanol. Okay, so this is going to be a nucleophilic acyl substitution reaction. We're going to substitute the nitrogen with an oxygen, the amide with an ester. And we're going to do that by adding some methanol nucleophile. Now we've talked in a previous video about how the carbonyl in an amide is not the most reactive carbonyl carbon. The oxygen there, the carbon there, and the carbonyl carbon is slightly positive. It's losing electron density to the oxygen and to the nitrogen. Moreover, in this ring, there's 90 degrees here, whereas this is sp2 hybridized, and so it would prefer to have 120 degrees around it. So that's another reason why this would be reactive. Unfortunately, though, it is not reactive enough to entice our weak nucleophile, our methanol molecule. Keep in mind that Me is a methyl group, so CH3. It's not reactive enough to entice the methanol molecule to attack it. So we have to make this, and the reason for that is because this lone pair on the nitrogen is allylic to the pi bond, and so through resonance it can donate its electrons toward the carbonyl carbon and stabilize the positive charge on it, as we discussed in a previous video. So this is not the most electrophilic carbonyl carbon that we could have. And in order to entice this nucleophile, this slightly negative oxygen atom, into attacking it, we have to make it even more electrophilic. Well, that's what this acid catalyst is trying to do. The brackets with the H plus in it, that's telling you we added a strong acid to this solution as an acid catalyst. That strong acid would take a methanol molecule and add an H plus onto it so that it becomes this conjugate acid of normal methanol. Sort of like hydronium, but with a methyl group on one side instead of a third H. Well, the slightly negative oxygen in the carbonyl oxygen can attack one of those slightly positive hydrogens, and the electrons holding it onto this sort of methanol is snap back and go to the oxygen to stabilize the positive charge there. So if you're thinking about what curved arrow pattern this would be proton transfer. And we're doing a proton transfer, as we've seen so many times before, we're doing a proton transfer in order to change the reactivity or stability of a molecule. This is not reactive enough. We can make it more reactive, a better electrophile, by doing this proton transfer. Once we do this proton transfer, we end up with an awesome electrophile. That lone pair turns into a bond to a hydrogen, and the oxygen now has a full positive charge. it uses that positive charge to pull even more electron density away from the carbonyl carbon, and now the carbonyl carbon has a pretty big partial positive charge. So you can see that it becomes a better electrophile after this proton transfer. Here, the oxygen is just pulling electron density away because of its electronegativity. But here it's pulling it away because of its electronegativity and because of the positive charge. So the carbon ends up losing more electron density. So we also have a methanol molecule here after we do that proton transfer. And now that we have this awesome electrophile, this pretty neutral, mediocre, apathetic nucleophile is enticed to attack. The oxygen in methanol doesn't have a full negative charge, so it's pretty content as it is, but because it's such an enticing electrophile with such a big slight positive charge, this oxygen comes in, attacks the carbonyl carbon, the pi bond breaks and goes toward the oxygen to stabilize that positive charge on it. And so if you were going to classify these arrows in one of our 4 curved arrow patterns, this would be nucleophilic attack, one of the essential steps in any nucleophilic substitution reaction. Now the carbon that it attacks, the carbonyl carbon, was trigonal planar, sp2 hybridized, and flat. But when the pi bond breaks, that same carbon loses its pi bond, so no longer needs a p orbital, and hybridizes the p orbital to help stabilize it. And now, what was the carbonyl carbon has only single bonds and is tetrahedral, sp3 hybridized and tetrahedral. So we have our famous tetrahedral intermediate. Okay, well, the charge tells you what to do. We want this nucleophile to stay on the molecule, and so we want to stabilize it. So we take another methanol molecule and we do a proton transfer. Anytime you want to change the stability or reactivity of a molecule, you can do a proton transfer. So if we take another methanol, the slightly negative oxygen on that methanol will steal the slightly positive hydrogen on what was our nucleophile. The electrons will snap back toward the oxygen where they can stabilize the positive charge. So after that proton transfer, we now have a stable tetrahedral intermediate. In addition to that, we have a methanol molecule that's been protonated, so methanol now with an extra H, and so a full positive charge. Okay, well, let me actually put that in blue. So at this step, we've added our nucleophile. So we've done half of this substitution. We've added the nucleophile. Now we just have to remove the leaving group. That was this nitrogen here. We have to remove that leaving group. The trouble is that that is not a good leaving group. It's already a base. If you force it to take 2 more electrons and have a full negative charge on an atom that is not that big, it'll be really unstable. It would just snap right back on. So it's a bad leaving group. We can make it a better leaving group. We can make it more susceptible to react, more reactive, by doing a proton transfer. The lone pair here on this nitrogen, which is slightly negative, can attack one of the slightly positive hydrogens in this protonated methanol that we have. The electrons that were holding the hydrogen there can snap back onto the oxygen to stabilize its positive charge. And that will turn this bad leaving group, not very reactive thing, into a good leaving group, a more reactive thing. So you change the reactivity of something by doing a proton transfer. So now, that lone pair goes to attach a hydrogen on here. The nitrogen has 4 bonds and therefore a full positive charge. And we have a methanol molecule floating around. That's what became of this. Okay, well now we have an awesome leaving group. So we had a bad leaving group here, now we have an awesome leaving group. This can accept electrons happily because it has a positive charge that it needs to stabilize. All it needs is this little push. And the carbon here that was before the carbonyl carbon is pretty slightly positive. After all, it's bonded to 3 electronegative elements, all of which are stealing its electron density. So it's pretty slightly positive, and the oxygen, the lone pairs on it, can feel that positive charge, and they're attracted toward it and try to form a pi bond in that direction. Now that there's a good leaving group, it can kick off the leaving group. And so if you're trying to classify this in curved arrow patterns, this is loss of a leaving group, the second of the essential patterns in any substitution reaction. Okay, well, after that step, we will have a double bond to this oxygen, which still has a hydrogen on it. It only has 1 lone pair. Because it has 3 bonds, it will have a full positive charge. We also have a methoxy group there. And on this carbon on the end, we have the nitrogen with 2 hydrogens on it. Well, we're almost done. The charge here just tells us one last thing we have to do. This is unstable because that's really reactive. And so what we want to do is to stabilize it, to change the reactivity of that molecule. So we can take the methanol we have here, and you can change the stability or reactivity of a molecule by doing a proton transfer. So the slightly negative oxygen on the methanol can steal this slightly positive hydrogen. The electrons can snap back onto the carbonyl oxygen to stabilize the positive charge there. And what you'll ultimately end up with is, I'm going to draw this a little bit more spread out. You have this carbonyl here. Instead of drawing this awkwardly going in this direction, I'm going to have the methoxy group going here. I have the 2 carbons in between, and then the NH2. So what was an amide is now an ester, and the nitrogen has left as an amine on the opposite side of the molecule. Now that is our final product. That is what they wanted us to explain how to make. We have that same thing all the way up here. You can see you have the methoxy group and then the NH2. So if we zoom out, and that was, so what we did overall was we burst apart a lactam ring. This could happen in a beta-lactam antibiotic, this nucleophilic acyl substitution reaction. And if we zoom out and try to get the full picture of what happened, and we look at the steps we took, you can see the 2 essential steps in any nucleophilic substitution: nucleophilic attack and loss of a leaving group. Everything else is just a proton transfer that either made a molecule more reactive and therefore less stable, or less reactive and therefore more stable. So for example here, this amide carbonyl carbon was not electrophilic enough, so we did a proton transfer to make it more reactive, make it more electrophilic. Then we could do our nucleophilic attack. Our nucleophile was neutral. After it attacked, it had a positive charge, so we had to stabilize that, change the stability of that by doing a proton transfer. Once we did that, we wanted our leaving group to leave, but it was a bad leaving group. It wasn't reactive enough, so we made it more reactive by doing a proton transfer. Now that it was a good leaving group, we could do have our loss of a leaving group, and once it left, we found that we had a positive charge on our carbonyl oxygen, so we did a proton transfer to stabilize that. So we had nucleophilic attack and loss of a leaving group to do the substitution, and to make things either more or less reactive, less or more stable, we had a bunch of proton transfers. So this illustrated how you could do a nucleophilic acyl substitution reaction to break open a lactam ring.